I got it. All right, I can click that. All right, so we're going to talk a bit about the temporal geochemical evolution of Africa's Western Rift. And I'd forgotten how exciting it actually all really is until I sat down to work on this. So how are we gonna, we're gonna click there. What I'd like to talk about today is first give a brief introduction to the geochemist's view of the African Rift, which I know is different from the geophysicist's view. We'll talk about the timing of volcanic activity because there's sort of an existing model that isn't actually supported by the data right now. I'll give you a snapshot view of the volcanic provinces in the Western Rift. Then there'll be about 8 or 9 or so slides of Western Rift geochemistry, the purpose of which is not to confuse you, but to show you that there are patterns and the patterns have meaning. Then I'm going to interpret it in light of, I would say, the geodynamic model, and then mention briefly some of the resource implications of this model. This is a map that I bet you have seen many, many times before. And from this simple image, we have the we have 2 different views of the continent with the location of the East African Rift running straight through it. And if from these simple images, it looks like there's this nice, straight, predictable crack that runs from the triple junction in Afar southward through Ethiopia, through Kenya and Tanzania to Malawi, with this sort of second spur over to the west side of Lake Victoria, which is where we're talking today. And from the data on the right-hand side, which show in millimeters per year, the plate motion vectors of extension between the Nubian and the Somali plates, you can see that the rates of extension are the greatest in the Afar province, 4 to 5 millimeters a year. And then they are slower in the 1s to 2s to maybe pushing towards 3 millimeters per year as we go south. So the old-timey model is one of sort of this north to south unzipping, that the plates are moving apart very rapidly in Afar and then slowest at the very southern tip in Malawi. But we're going to find that's not actually the case. In this view, the dashed white lines encircle the 2 regions of topographic uplift along the East African Rift. And we see immediately that some simple linear model isn't really going to do the trick. The 2 domes, the Ethiopian and the Kenya dome, are separated by the Turkana Depression, which is where the older northwest to southeast trending Anzagraben intersects the modern rift. And that's also where the earliest volcanism occurred 45 million years ago. The part of the volcanic sequence that's the best studied and the best known is that which happened in Afar 30 million years ago, and that's the flood basalt sequence, which is mostly in Ethiopia, but a little bit over on the Yemeni side of what is now the Red Sea as well. So what we find when we look a little bit more closely is that the time period around 20 million years ago was one that was very busy, and there was very widespread activity, both physical and volcanological. So the rift basins propagated to both the north and the south from Turkana 20 million years ago, eventually connecting in the north with the rifting in the Afar province and initiating extension along the eastern rift, which is shown here in the pale blue. What is less well recognized, and this is where the recent data have been really critical in helping us understand, is that that same time period showed the onset of volcanic activity in the western segment. So at about 20 million years ago, the whole rift really became active and magmatically so. The reason that this is new is that a lot of the older dates are from potassium-argon radiometric information, and argon is a gas, and so the dates are not always as reliable if things get hot. And if you're in a magmatic area, things get hot. So the more recent work, which was done in that southern tip by that letter R in the Rungwe Basin, showed that there was uplift and erosion well before 20 million years ago, perhaps 40 million years ago. And uplift requires heat, heat requires magmatism. So we know that there was the onset of magmatic activity throughout the rift at about the same time, but by 20 million years, there was a lot of activity. And each of the volcanic provinces has some of these 20 million year old lavas, and each of the 3 of the 4 provinces have very recent activity as well. So despite the similarity in the age of magmatic onset in the eastern and western sides, there are very clear and fundamental differences between the rifts and the lavas and their geochemistry. The first order thing that we observe is that the amount of green on that map, and green is the area covered by lavas, that green area is much bigger in the east and much smaller in the west. And that tells us that the processes leading to magmatism are different. And it also kind of predicts that the lavas themselves are going to be a little bit different. Each one of those little red triangles is a well-established volcanic center. When we look the image on the right, that shows, and I'm guessing this is one that's familiar to you, this shows the past few decades of earthquake locations along the East African Rift. So similar region, hopefully identical region to the map on the left. We've got the earthquakes that define the Afar region and work their way southward along the rift. And you can see that you could even, if you were to do it on the basis of the seismicity, you would draw the main axis of the rift through the Western Rift. And as a Western Rift researcher person, I, of course, feel very, very happy about this. So let's look at the volcanoes of the Western Rift. There are 4 individual provinces, and each one is distinctive in the morphology, the shapes of the volcanoes, and the geochemistry. This is an area where the British colonial folks came and did a whole lot of sampling and a whole lot of research, and they came up with so many different names for all of the different lava types there are some geochemical similarities, but the nomenclature of igneous rocks from the British than the Uganda Geological Survey is more extreme. There are more rock types named on the basis of individual craters from the Western Rift province than from any other region in the globe. And that tells us that there are lots of subtle, small scale differences. In Toro Ankole, we're going to see in a minute, there are explosion craters and very few lavas. As we work our way southward, we find in Virunga, there are centralized volcanoes and isolated craters. In Kivu, we just have lavas, but when we get back to Rungwe, we have the big central volcanoes and some lavas and some explosions as well. So there will be sometimes when the geochemistry is unpleasant. I know that. So let's look at each one of the provinces. This is an aerial view of the Toro Ankole province, and it's made up of several small volcanic fields, which are shaded in sort of the dark gray over on the left-hand side. And they are Fort Portal and Katwe Kikarongo and Bunyaruguru. And they are, each one, again, is very, very different from its neighbors, but what they all have in common is they are characterized by small overlapping explosion craters. And we see it in the sketch map that is in the middle of the Bunyaruguru volcanic field, and we see it beautifully in the Katwe Kikarongo explosion craters composite aerial view on the right-hand side. And there are very, very few lavas that flow over the surface because the whole region is full of explode this, explode that, single shots out of the ground that don't leave beautiful flowing lavas. So immediately, as a geochemist, we look at this and we say, oh, volcanism here involves a lot of volatile elements. There must be a lot of water and a lot of carbon dioxide, because those are the elements that contribute to volatile budgets of magmas that cause explosion. So that's our first piece, is that we know that we have a lot of volatiles, carbon dioxide, and water in the north. When we move a little bit south to Virunga, we find several large central volcanoes, and each one of those are shown with a white star on the map. And then 2 or 3 regions that I've circled in red where there are very small individual explosion craters. So the 2 western volcanoes, Nyiragongo and Yamuragira, are active. The other white stars appear not to be, and those explosion craters are less than 100,000 years old. So even though volcanism started 20 million years ago, these major volcanoes are on the order of 10 million years or less, and some aspects of the volcanism are very, very recent. There's even, I would say, a change in style of volcanism to include more of these very small craters that are abundant in the past 10,000 years, in particular. When we look at the morphology of Nyamuragira on the right and Nyiragongo on the left, we know that their shapes are very, very steep, and we're going to see other volcano shapes that are not quite as steep. And that's because they are very persistently active. They have a lot of little eruptions. They also both have active lava lakes. And the lavas, when they erupt, move very, very, very quickly across the landscape. This is something that I think most of you know very well. The reason they do that is because of their geochemistry. And they have a lot of potassium and a lot of phosphorus. How much is a lot? In real terms, not that much, but so much more than other volcanoes around the world. So the potassium and the phosphorus are elements that are known to break down the polymerization of the melt. So their presence causes the melts to be very low viscosity and to flow very, very rapidly. They also produce very fertile soils. The map at the top here shows the pathways of a few of these recent lava flows, and you can see them because they're dark against the green background. And you can see how it looks like someone has simply poured water on the landscape. And that's the potassium and the phosphorus that cause these liquids to flow so rapidly. We see on the lower picture one of the craters at Bunyaruguru, and that reminds us that even though we've moved south from the explosions only situation at Toro Ankole, we still have a lot of small, rapidly eruptive, volatile rich flows here in the Virunga province. We also know that in the lowlands around Nyiragongo and Nyamuragira, there are many mazuku, the evil winds, the craters through which a lot of carbon dioxide gas is emitted every day, all day. So again, even though we've moved south from Toro Ankole, where everything was carbon dioxide driven, there's a lot of carbon dioxide present in the lavas in this area. The third province moving south is South Kivu province, just located south of Lake Kivu. And my personal feeling, not that anybody ever asked me, is that it is really an older part of the Virunga province, and that maybe this is one large area because there are a lot of older lavas, older, let's call it again, 10 to 3 million year old lavas. Those are the blue lavas in the south part of the picture in the Kivu area. And then the pink lavas are much, much younger. They're mostly in the couple of million years as we move toward the north. And the Kivu province is also distinguished by not having a lot of explosion craters. We find lavas that cover the landscape that flowed much more slowly than those of the Virunga province. They do not have quite as much potassium. They do not have quite as much phosphorus. They make beautiful landscapes that look old, right? They look geologically, well, to a volcanologist, they look old. We do not see explosion craters. We do not see young lavas. We see lavas that have had a chance to have plants grow on them. And that just tells us that, that South Kivu is a little bit older than the lavas in the Virunga province to the north of Lake Kivu. And again, the fact that they are lavas that did not flow like water on the landscape tells us that they have a bit less phosphorus, a bit less potassium, and there's much less of a role for carbon dioxide here. We will be tying all this together, don't worry. Finally, at the southern end of the Western Rift, we have the Rungwe province, and it's special in my heart because I did a lovely field season there, but it's also special because it's at the junction of the Eastern Rift, going off to the northeast in the map, and the Western Rift, and I've got that Rungwe big capital blue R where the age dating was done. So we have the opportunity in the Rungwe area to really tie together a long history of volcanism and sedimentation. And Rungwe is made up of 5 big volcanoes, and those are the 5 red stars in the enlargement on the right. And what's interesting there is that each one of them is geochemically exceedingly different from the others. We don't entirely know why, but we keep having this pattern, right? That everybody is different from their neighbors. And that's geochemically very important to understanding how the rift got to be. Rungwe in the middle has a lot of very, very light colored lavas, very what we would call evolved lavas that have sat in the crust for quite a while. The cone near it, Tukuyu, just to the south, they're all very, very low viscosity flows. Again, extra potassium, extra phosphorus, and Kiejo, the youngest, has quite a bit of explosive activity, suggesting that volatiles are important here. There's again abundant carbon dioxide seeping out of the ground. And I have a memory near the town of Mbeya of a Coca-Cola bottling factory that is capturing this carbon dioxide coming directly out of the ground. So that tells us that there's a lot of carbon dioxide activity. Here's a picture of the crater of Ngozi volcano, where there are a little bit of hot springs, but nothing particularly overwhelmingly warm. And then the Kiejo volcano on the right. And the only important thing for you to notice is that it just looks like it has a different shape than Nyiragongo and Yamuragira. And that tells us that even though these volcanoes are all in the rift and they're all pretty darn near one another, they are chemically really, really different. So a brief overview summary is that and this is the part that I would love for people to be able to relate to, and then we're going to get ugly with the chemistry. Every area in the Western Rift has explosion craters, and that means there's carbon dioxide getting to the surface in a hurry. Most of the areas have a lot of low viscosity lavas, and that tells us that phosphorus and potassium are important and are present in abundant quantities. None of the areas have huge hot springs. There are many, many continental volcanic areas in Italy and the US, even in the Eastern Rift, where every volcano has nice hot springs around it. Not at all in the Western Rift. So and we note that the volcanic provinces are internally heterogeneous, by which I mean every volcano, and in some cases every lava, is different in shape and chemistry from its next door neighbor. None of these things are expected. None of these things are common. So I want to spend some time talking about how they got to be that way and how we interpret them, because that's important for understanding the resource potential and also understanding the geophysical data that I would love for you to go and collect. So if you're not a chemist at heart, and I appreciate that most people are not, this is the slide that really matters, right? That there's volatiles, carbon dioxide, potassium, phosphorus, but not a whole lot of hot water, and everybody's different. We care about the geochemistry because it can tell us about processes. And when we start thinking about the processes, geochemists say, well, we've got a bunch of black rocks. They're all grossly, we call it basalt. They have between 6 and 10 weight% magnesium. Let's look at our rocks and compare them to the global oceans. Why do we do that? Because the ocean basins cover like 70% of our planet. And the rocks that we find there are profoundly boring. The rocks that we find there are very, very, very similar anywhere in the world. So I've got a graph here on the left that shows truly thousands of data points. And I put a blue box around the chemical range that we care about. And what you can see is the data form really, really, really tight clouds. It doesn't matter what the data are. There's iron, calcium, alumina, sodium, titanium. That's lovely. The point is that these clouds are really dense. And there are clear trends, but everybody looks alike. And that's because mid-ocean ridges, where these lavas are generated, sample everywhere the same process. They sample the shallow mantle as it convects. So there's upwelling beneath mid-ocean ridges as the asthenosphere decompresses and moves upwards, and eventually it melts and it spits out lava that looks the same everywhere. And so the ocean, 70% of our planet is covered in one rock. To somebody like me who loves the Western Rift, I call that boring, but it still tells us about how our planet works. So the key feature for us to remember is that the Western Rift lavas are never boring. This diagram shows the chemical composition of the of the rocks in the oceans and in the Western Rift. And we plot silica, which is the most abundant element in these materials. And we've plotted sodium and potassium because they are alkali elements. They're a +1. They are over on the left-hand side of the periodic table. And we pay a lot of attention to them because most minerals don't like them. Most minerals associated with the types of lavas that we find don't like them. So this plot here shows a very small red area that has about 15,000 data points in it. Those are our boring mid-ocean ridges. And I apologize if I offend anyone who loves the data. I kind of secretly do, but the blue area is only about 150 samples. And that blue area is huge. And that's the point of this diagram, is that the amount of chemical variability in the Western Rift is enormous. We saw that in the morphology of the lavas and of the volcanoes themselves. But when we start to look at their geochemistry, we say, oh my gosh, what a mess. We say that a lot in my research group. We say, oh my, what a mess, a lot. So we also find that these Western Rift lavas have a lot of sodium and potassium. We already knew they had potassium, but they have sodium too. Okay, brace yourself because this looks ugly, but it'll be okay. This diagram is, I would say, one of the favorite ways that geochemists have to confuse people. And just like you all will get up and show me a checkerboard diagram to show me how good your geophysical models are, this is sort of the geochemist's equivalent of a checkerboard diagram. It's got a lot of data on it and it confuses the heck out of people, but it's actually pretty simple. The x-axis is a bunch of elements, and they are arranged from the left. We have elements that the mantle hates and that most basalts hate. And then as we move over to the right, we have elements that the mantle and basalts don't hate quite so much. So we find, and we plot on the y-axis our data, and it's normalized to the mantle that gave us mid-ocean ridge basalts that covers 75%, 70% of the planet. So the red line there shows all of the data for mid-ocean ridge lavas. And the thing that matters about the red line is that if you take metric truckloads of data for the mid-ocean ridges and you plot them, you get a very smooth curve. You get a smooth curve because we arranged the elements so it would give you a smooth curve, and that's fine. That's our little trick. But mid-ocean ridges, global oceans, smooth red curve. Mantle plumes like the rocks in Afar or the rocks in Hawaii or the rocks on many islands, pretty smooth, but slightly different patterns. So that's what I want you to hold in your mind when we move to the next slide, that all the oceans give us a smooth pattern of a very distinct shape, and the ocean islands or the mantle plumes give us a pretty smooth pattern of a different shape. Okay, so here's the Western Rift. Doesn't look like that at all, does it? And this is the only point of this slide. Don't try to figure out who's going up and who's going down, because it doesn't really matter to us for understanding the Western Rift geochemistry. What matters, particularly what matters to a geophysicist, is that there are a whole lot of daggers and spikes and ups and downs and pointy things in each one of the Western Rift provinces that don't look like the oceans or plumes at all. The top left shows us Rungwe, and the lavas there have a pretty narrow range, but it goes up and down and up and down and up and down. In the Kivu province, it's more smooth, but it still doesn't look like anybody we find in the rest of the world. Bufumbira in the Virunga province and Toro Ankole, it's up and down and up and down and up and down. Oh my God, what do we do with all of this up and down data? Okay. First, we take a deep breath and we say, okay, all geochemists are crazy. That's fine. And then we say, well, wait. We understand how the oceans work. We understand how plumes work. And what we see here is that the Western Rift lavas don't work like that. Why is that? We can figure it out. All of those ups and downs and all of those wiggles tell us that the minerals that are present beneath the surface, the minerals that are present in the mantle that melts to give us these wacky lavas, are really different than what we expect in the bulk of the world. in the bulk of the mantle. We can play games and look at the individual minerals because look at the individual elements, because every mineral likes specific elements. And so we can tease it apart. And when we do that, we find that in the Toro Ankole region, we have really strong evidence that there's a big carbonate influence. We knew that from seeing the CO2 explosion craters. We know that there are amphibole and phlogopite, which are two dark minerals that have water in their structure. So again, carbon dioxide and water. And then we find these funny minerals like titanite, which I grew up calling sphene, and that might be a familiar name, but it has, as you'd guess from its name, a lot of titanium, apatite, which has phosphorus, zircon, which has zirconium. So what you would take away from that laundry list of minerals, and we'll go further with it in a minute, is that they are not common. They are common in the Western Rift. When we go to Virunga, we find, again, the mantle beneath our feet has carbonate and amphibole and phlogopite. And in Kivu, it has amphibole and phlogopite. In Rungwe, carbonate, amphibole, again, ilmenite, apatite, and zircon, titanium, phosphorus, and zirconium. We also find evidence that all of these areas are underlain by material that has a lot of pyroxene. Again, who cares? We care for a bunch of reasons. The first reason that we care, and I put up a couple pictures of agriculture in these provinces, because these minerals that are down beneath the surface that lead to the melts that have the wacky chemistry, those processes form very fertile soils. The amount of, if I'm building a garden here in Pennsylvania and I want to put some fertilizer on my soil, I will use carbonate and I will use phosphorus. In these volcanic provinces, you have that coming naturally out of the ground. And also these minerals, these mineralogies tell us about the history of the land underneath our feet, of the mantle. And I keep using the word here, metasomatism. What on earth does that mean? It means that there have been fluids that have traveled through the lithosphere that have changed the mineralogy and the chemistry of that mantle lithosphere. This region has been fluxed with carbon dioxide, with water, with silicate melts, like kind of normal lavas, and with the material that generates kimberlites. Oh, okay. Where do those come from and what are the implications? The most important implication, when you see the word kimberlite, the word that kind of ought to flash through your head is diamond. Right. And indeed, in the Toro Ankole area, where we have the greatest presence of carbonate, the greatest evidence for carbonate involvement for carbon dioxide, there are apparently tiny, sparse, industrial grade diamonds. So not enough to sell and get rich and make jewelry, but it tells us that they exist in that area. Where these fluids came from really has to do with the 2 billion year history of the region, about how the African continent was put together by various geological events that involved building mountains, removing ocean floor, the terms of subduction, if that's a familiar term to you, but the insertion into the mantle of fluids that used to be on the ocean floor. Think old limestone coral reefs that gives you both water and carbon dioxide. Silicate fluids derived from sediments that have been subducted, that have been forced beneath the Earth's surface. They all give off fluids. Those fluids are in the lithosphere beneath the Western Rift in quantities far greater than we find beneath the Eastern Rift, and much, much, much greater than we find beneath Ethiopia. And again, nothing like what we find in the vast majority of our planet, nothing like the oceans. Geochemists have another tool that we use. We look at isotopic data. We look at elements that have naturally occurring radioactive isotopic compositions. This graph happens to plot strontium, which is related to rubidium, and neodymium, which is related to samarium. Oh God, it's all those words. Basically, what this graph plots is the influence of elements that most rocks hate, plotted against the influence of elements that some rocks like. And when we look at the data that is plotted here, I just want you to see pattern-wise that there's this tiny little gray box right up in the left-hand corner. That's 75% of the planet. And then you look at all those colored boxes and you're like, oh my gosh, the Western Rift volcanic centers have geochemical signatures that are frankly all over the map. Each province, and they are small, has a greater range of isotopic composition than all of the rest of the planet. Congratulations, how do you do that? I mean, it's really remarkable. Like that variability in Kivu, which is larger than the variability in thousands of square kilometers of ocean floor, that variability exists over a distance of 20 kilometers. That's shocking. The variability in Virunga, again, 20 kilometers different distance separates all of those analyses. We can tease it apart. We can make sense out of it. I know you can do other isotopic systems, but this one I picked. And what it reflects is there's this one sort of center of the geochemical universe that I put in as this yellow star, and all of the volcanic provinces in the Western Rift have a touch of that, and then somebody else that's different. And it's sort of like bicycle, we think of it as bicycle spokes. You got that yellow center of the bicycle wheel, and then in Kivu, a bicycle spoke leads you toward mid-ocean ridges, and in Rungwe and Toro Ankole and Virunga, the other bicycle spokes lead you in other crazy directions. What matters is that we see very, very large isotopic differences over tiny distances. And we interpret it by acknowledging that what we must be sampling by volcanoes that are right next to each other, what we must be sampling is very, very, very heterogeneous. And the easiest way to make it heterogeneous takes us immediately into geophysics. And that heterogeneity, that geochemical craziness that we see is likely related to very, very steep, abrupt topography on the boundary between the lithosphere and the asthenosphere. How do we get that topography? We know we are rifting, and we know that when we make a rift, we have to thin the lithosphere, right? We don't have a choice. We don't really understand how we thin the lithosphere, but the lava chemistry tells us some things about it. What it tells us is that we aren't gradually burning a hole through the lithosphere with some fierce mantle plume. We don't see any evidence for that. What we think is happening is that as we stretch the lithosphere a little bit, blocks of it break off and fall. And that process produces the crazy lava chemistry that we see. So we know the topography on this boundary that is associated with extension, that it's associated with rifting, has to be steep, and it has to be steep and variable over tens of kilometers. That's nothing. So we think that we interpret the chemistry that the rifting triggers the falling off, whether it's laminar process, delamination, a gentle process, or foundering, abrupt breaks. Pieces fall off and they melt as they sink through the asthenosphere. Again, this is very different from mid-ocean ridge basalts. In mid-ocean ridges, we have a lovely upwelling of the asthenosphere. And in the Western Rift, we have, I think, a falling down of the very thick lithosphere as it tries desperately to get thin. That foundering may be ductile. We call it delamination. And that all of the geochemistry that we saw, the metasomatized compositions, they're very, very heavy. They're heavier than normal mantle. They're heavier than normal lithosphere. And if you start triggering them with earthquakes or triggering them with rifting, parts of that lithosphere will detach and fall. They can do it in a ductile form like this, or they can do it in an abrupt form like on the previous slide. But it seems that the lithosphere in this area gets thin by shedding parts of itself deeper into the earth. The geochemistry is what tells us this. I think this is the last weird chemical slide. Be patient, sorry. The other evidence that we have for this is that we see so much carbon dioxide that is involved in all of the eruptions. And the only place that you can get carbon dioxide is at the deepest part of the craton. And by having steep topography, steep breakage-induced topography along the margin of the craton, that releases carbon-rich fluids that percolate upwards through the crust and generate the explosive lavas that we have. One good piece of evidence that we have for this process is the existence of the Ruwenzori Mountains. The Ruwenzori Mountains are this, big square block that kind of popped up out of the surface a few million years ago. And the only thing that makes Earth's crust pop up is if something heavy has fallen off of its bottom. And so the uplift of the Ruwenzori is another line of evidence that tells us that the lithosphere is shedding itself in order to accomplish the process of rifting. And that process is what gives us the wacky chemistry that we have. If we try to put together a history of the Western Rift, we know that one of the metasomatisms, one of the mountain building processes happened about 1 billion years ago. Another one, 450 million years ago. And today, that thick lithosphere is being thinned by extension, and it's being warmed by the presence of the mantle plume that feeds the lavas in Afar. But it is that lithosphere that is so heterogeneous and so chemically weird, it melts and it gives us these crazy lavas that we have at the surface. And maybe you can see from the schematic image on the right that each one of those blue triangles, which is a Virunga volcano, is located at a slightly different position relative to the weirdly chemically metasomatized lithosphere and that topography of the lithosphere-cenosphere boundary. So each volcano is geochemically different, and each of them are weird compared to the oceans. But this modern volcanic picture leads to predictions of crustal structure that you as geophysicists are going to resolve for us. You already have in some cases for the Ruwenzori. So this weird structure is what leads to the chemistry, and the chemistry is what helped lead us to that interpretation. And then the question is, okay, well, what about resources? Can we in the Western Rift benefit from this? The answer is probably not as much as I wish it were. We know that there is some oil and gas production because any rift basin has a lot of sediment, and you're in a very productive organic area. So there's a lot of plant material that can fall into rift basins, get covered with a lot of sediment and heated. And that does lead to natural gas production. And there is some of that, and that's good and important. As far as geothermal and hydrothermal energy, I am less optimistic. I have a picture at the bottom of a geothermal plant. And I don't think that we're going to find in the Western Rift those same kinds of resources. When lavas explode, because they are propelled by carbon dioxide and water, they move quickly through the crust, and they don't sit around and interact with groundwater in a way that makes for major hydrothermal circulation. I would love to see more and more and more big hot springs that say, oh, we've got a great place to put a hydrothermal plant or a geothermal plant. But the brittle breaking and the foundering, the abrupt thinning of the lithosphere seems not to support this type of energy production in a very big way. I think there are some resources, but my prediction is it's not going to be like the area around Lake Naivasha in Kenya, or the areas in Iceland, or the areas in around Yellowstone in the US, where you have abundant water interaction with shallow volcanic systems. Most of your lavas come up rapidly because they are propelled by volatiles. There would be some, the good thing, the high potential, is that some mineral resources may be abundant because the metasomatic phases, these weird weird minerals that we find and the weird chemistry, we know that there are high contents of rare earth elements, high contents of titanium, and there are some high contents of other elements. But as we move towards lithium batteries and rare earth element extraction and the need for titanium in metal production, there is a good likelihood that there are places where small scale mining operations could be really, really, really productive. That raises, the obvious environmental issues of whether one wants to do that. But because these elements are weird and they exist in lavas whose geochemistry is weird, their abundance and their productivity might just be very, very important. And I'm going to close with, again, a reminder about agriculture. And, one of the things that I have loved the most when I've been in Rwanda and Zaire and Tanzania is the incredible productivity of the soil. And that is, again, because of these weird elements that exist in the weird minerals that come from the weird history, the weird 2 billion year history of the mantle in your area that leads the place to be so productive for the growing of crops. So that's what I had to say. And I know it's a lot of geochemistry, and I know that a lot of it doesn't make any sense at all. And it's really challenging for me to try to interpret as well. But the points are, you have I sound like a kindergarten teacher. Each one of your volcanoes is indeed chemically very, very, very special. Each one is different. It means that the solutions for resources are going to vary from volcano to volcano and nation to nation and province to province. It means that the research questions for geophysicists about the presence of fluids and the nature of fluids and the topography on the lithosphere, asthenosphere boundary, those questions are important. And those questions are right now questions. And it is really exciting that you are here right now to use geochemistry as a guide to address those questions. So I will stop and I will ask for your questions, because you are the ones who know where your interests are. And I'm hoping that any small piece of what I said is someday useful to someone. So thank you.
Yeah, thank you very much for this brilliant talk and thought-provoking about how the Western Rift is functioning, Tanya. Thank you very much.
You're welcome. I know it's a complicated area, and the solutions that will come from geophysics. They will come, we now have a geochemical framework for what is there, when it got there, and how it got there. And now it is to you to help figure out what to do with it.
Yeah, I think so. So is there any question? You can write your question in the chat or unmute yourself.
Or you can unmute, you can shout. It's like family dinner. You can say anything.
Yeah.
And I will also put a question to you, because I have not been everywhere. Are there geothermal hot springs and resources that people are trying to produce?
Mm-hmm.
No, I'm seeing a shaking of the heads.
Yeah, unmute yourself, Harry.
Please, Harry.
So I'm not Harry. I'm just Kareem using the computer. Thank you very much. That was extremely educational for me. I mean, I'm not a geochemist myself. It's really great to listen to your talk. I mean, just correct me if I'm wrong. Then the argument here is that maybe the process that you're alluding to is the interaction between your mobile belts and the cratons.
Yes.
And then would you be happy if the variability is within this very high frequency variability is explained by maybe different metasomatic events, or how would you feel with this? And as far as thinning the lithosphere is concerned, I've been consuming a very nice paper that was published 2015 by a team with Van Hoenen, your own, where he was showing that fluid melt rock interactions during the mantle metasomatism are really weakening the lithosphere
Yes,
more than the impact of the plume. So
yes,
that maybe this would reconcile a little bit, maybe what you're alluding to.
absolutely.
That was nice. That was really nice for me.
I mean, you asked would I be happy? I would be happy any day we understand anything, right? I mean, I think the mobile belts, we know the mobile belts are really heterogeneous, right? They have all sorts of lithologies. And when we overlay on that, what you just said, the metasomatism weakens the rocks, and the metasomatism is fluids moving in and through and between and making veins. And so everything is heterogeneous. And then you crack that and you can sample great depths. You're sampling all kinds of heterogeneities. And I think that's what we've finally understood over the past few years, is how the heterogeneities got there and how it is that they are exposed for us to sample.
Right. So I'm just, I mean, if there's no one else asking a question, then I can just, I'm just very much worried by the delamination that you're using. I mean, delamination, I mean, in geophysics, we tend to be a little bit more careful. I mean, if you talk to someone like Peter Molnar or Greg Hausman, they would be very happy with the blobs that you have. I mean, with the erosion, and then delamination would be maybe something like an extreme case of those erosional features that you show in the blobs. But I wonder whether, I mean, maybe we're missing someone that does geodesy at within the Western African Rift to see whether there is anything that would get into those length scales that you're talking about.
I would love it if you would do that. I'm counting on you.
That's another deal. Thank you so much, Tanya. That was really nice listening to you.
I have a student who's working on a similar problem in Saudi Arabia, and they happen to have beautiful geophysical data that shows a block that is not attached. In the Western Rift, because of obvious reasons, it has been difficult to do that kind of detailed geophysical study. And I think, again, you guys are in Rwanda, you're at the perfect spot. But I would also say, I mean, that the mechanism of thinning the lithosphere in practical terms matters less than, say, the resource potential. For me, who has the luxury of getting to think about these things frequently, that's very different from being in an area that is trying to develop its resource potential. And I think exploring these questions with a focus of how thick is the lithosphere, what is the fluid, where are there fluids now, and what are they doing now? I think, I mean, I would love to have, a small scale tomographic study or geophysical, but what I would love and what is needed globally are probably different things. We joke that my phone never rings with someone saying, Dr. Furman, we have a case of mantle heterogeneity that is unexplained. Could you please help us? Nobody cares. But I think some of what we have learned turns out to have implications and applications.
Is there anyone having another question? Okay, so I just have a small one about if we remove the influence of the mantle plume, how is that conceivable?
So geophysical studies to date have had a hard time in the Western Rift showing that it crosses the 660 kilometer discontinuity. We see little warm pockets beneath each of the volcanic areas, but from everything I've seen, we don't see a compelling, convincing connection between shallow manifestations of warmth and the deep plume. That is one point. The other point is that when we look geochemically, and particularly when we look at the helium isotope signatures, which I realize people, but they're at least they matter. We don't see evidence that requires a physical contribution from the mantle plume. We see evidence of heat and of melting that a plume is inducing, but we don't see, stick a straw into it and suck magmas out the top. So I think it's there and it's important, but it isn't.
It does not underplate.
It's not the only game.
Okay. Okay. Thank you. So I think
I would say I want to thank you all for listening, and I know that asking questions in this format, particularly of a geochemist who showed so many ugly pictures, I know that's difficult, but if you percolate on it and you think on it and you want to ask, you can reach me by email anytime.
Thank you. Thank you very much.
I would enjoy that.
Well,
And I would love to, I would hope that when you finish your master's degree, if anybody's interested in a PhD, please consider Penn State. We would love to have you.
Thank you. That's very good.
All right. Congratulations to you for all that you're doing.
Okay, well, thank you. Thank you very much for this brilliant talk and very pedagogic. Thank you.
Well, thank you. Thank you so much. Bye-bye.